Hello everyone, welcome back to my channel. Today we are starting a new lesson which is chapter 3 logic gates. In this lesson we are going to learn about the basic gates, derived gates and also how to draw a logical diagram for a given boolean expression. So all this we are going to learn. This is a very small chapter. Probably we are going to finish it in 2 sessions. Okay. So the objective of this particular chapter is to learn the different types of gates and also design the logical circuit. Okay. So whenever we say a logical diagram or a logic gate, what does that mean? A gate is simply an electronic circuit which operates on one or more signals and always produces an output signal. Now, why is this gate required? These gates are nothing but we have learned all this Boolean algebra in the previous lesson, isn't it? We are going to use these gates in order to build a circuit to perform those operations, to perform certain operations. Okay. So in the coming sessions, we are going to learn how to draw these diagrams. So these diagrams are nothing but the actual circuits. Okay. So we are going to use these gates in order to build a circuit in order to get a required output. So a gate is simply an electronic circuit. Like I said, it is nothing but a circuit which operates on one or more signals. As in, we have to give input signals to these gates, then only they will provide an output signal. Then what are these output signals is depends upon what type we want, and that is what we are going to learn in this lesson. If we want to get a certain type of an output, how are we going to get? What are the combination we require to make, and so on. Okay. So gates are digital circuits because the input and output signals are either low voltage and high voltage. Okay. So gates are digital circuit. It will have two states, that is either high or low. Now whenever we are saying that we are giving input 0, which means nothing but low voltage. Okay. So whenever we say we are giving input as a 1, you should understand that in a digital language we are saying that we are giving a high input. So whenever we are giving a high voltage, it means we are giving 1 as an input, and whenever we are saying we are giving a 0 as an input, which means we are giving a low voltage as a input. Right. Now gates are often called logic circuits because they can be analyzed with Boolean algebra. Okay, so these gates, which are nothing but the digital circuits, are called as logic circuits because they can be analyzed with Boolean algebra. Now we have learned this Boolean algebra, isn't it? So what do we do in Boolean algebra? Boolean algebra, we take Boolean variables which have values zeros and ones, isn't it? So all this we have learned in the previous lessons. So we can implement them using these gates. Okay. So these gates are also called as logic gates because we can implement Boolean algebra with them, or we can analyze them using Boolean algebra, isn't it? So let's see what are the gates which we are going to learn in today's session. So there are two types of gates, okay? Basic gates and derived gates. Like the name says, basic gates are nothing but the very basic gates, and derived gates are the one using the basic gates we are going to derive them. They are a little bit complicated ones, okay? So which are these basic gates? Basic gates are mainly we have NOT gate, which is also called as an inverter gate. Then we have OR gate, then we have AND gate. Right, there are three basic gates. Now, when it comes to derived gates, there are four derived gates, which are NOR gate, NAND gate, XOR gate, and XNOR gate. So in today's session, we are going to learn all about them. So what does this each mean? How do we write a logical diagram for these, and what are the truth table? How to draw a truth table for the respective gates? That is what we are going to see in today's session. Okay. So let's go ahead and see the basic gates. So the very first one, which is inverter gate or a NOT gate. Okay. So what does this NOT gate mean? An inverter gate is a gate with only one input signal and one output signal. The output state is always the opposite of the input state. So remember, inverter gate or a NOT gate is the only one which takes only one input. Okay. Rest all takes two or more inputs. Now this is how we represent them. We have come across these gates briefly in the Boolean algebra lesson also. So I hope you all remember that. Okay. So this is how we write a triangle and a bubble. So whenever you see this, you should understand this is nothing but a NOT gate. And if at all we give any variable as an input, it always gives its complement as a output. This is the speciality of a NOT gate. That is why it is called as an inverter gate. It inverts the value. Okay. So you should remember there was a question asked also, which gate is called as an inverter gate. So you should know it is a NOT gate. Okay. So here, see here the truth table. When you give a low voltage, the output is going to be the high voltage, and whenever you give a high voltage, it is the output is going to be the low voltage. Okay, in other terms, I said low means 0, high means 1, isn't it? So if we give 0 as an input, we are going to get 1 as output, and if we give 1 as an input, then we are going to get 0 as a output. Fine. So this is about NOT gate. Next we are going to see is OR gate. Now what is this OR gate? The OR gate has two or more input signals but only one output signal. This you should remember. We can give more than two. It cannot have one like how we used to give for NOT gate. It has to have two or more. It can be of any number, but minimum is 2. But the output produced, irrespective of how much ever the input values are, is going to be only 1. Okay, so if any output signal is 1, the output signal is 1. Okay, so if at all we have, even if we have all zeros but then only one value is 1, even then the output is going to be the 1. Okay, this is the speciality of OR gate. Fine. So let's go ahead and see the truth table for the same. So we have here 2 input OR gate and we have 3 input OR gate. So in a 2 input OR gate, what is going to happen is we are going to take 2 variables. So this can go on. Okay, so it is not that it has to be 2, 3. It can be 4, 5, 6, etc. But we are going to see only 2 and 3. Rest you can try yourself. Right. For 2, how are we going to write the truth table? We have learned this. The values are going to be 0, 0, 0, 1, 1, 0, 1, 1. And we have already seen that for a OR gate, if any one value is also 1, then the output is going to be 1, isn't it? So very first combination is 0, 0. Neither of them are 1. So the output is going to be 0. Okay, for rest all, you can see there is at least one input whose value is 1, isn't it? That's why we are getting 1 as an output. Similarly, for a 3 valued input, see here x, y, z, the combination we are going to write something like this, that is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. Okay. So the output is going to be wherever there is all zeros, only those value is going to be 0. Rest all is going to be 1. Why? Because at least one of the input is 1 here. So that is how we are going to remember the OR gate. Fine, this is all about OR gate. Next, AND gate. So what is this AND gate? The AND gate can have 2 or more input. Even in the case of AND gate, we have to have 2 input and more. We can have more, but only the NOT gate is the one where we can have only one input. Okay. Now it produces one output signal. Okay, irrespective of how much ever input you are giving, it is going to produce only one output. When all the inputs are high, the output is high. So in this case, in order to get 1 as an output, all the input should be 1. Even if there is 1 0 in the input, then we are going to get the output as 0. Now this is AND gate. Okay, so you need to remember this difference between OR gate and AND gate. Let's see the truth table of them. Okay, these values I'm not going to explain again because you should know. Now here, the very last one is the only one which has both the inputs as 1, isn't it? That is why only for that the output is 1 for AND gate. Okay, in other places, there are at least 1 zeros everywhere, at least 1 0. Okay, it means it includes even 2 zeros also. Then for those values we are going to get 0 as an output. Similarly, for the 3 variable truth table also, wherever there is at least 1 0, all these places have at least 1 0, the output is going to be 1 for the output is going to be 0. Wherever there is at least 1 0, the output is going to be 0. Wherever there is all ones, only then the output is going to be 1. So this is how an AND gate works. Okay. So this is NOT gate, AND gate and OR gate. We have seen how to draw them. How do we write the truth table for them, isn't it? Next, let's move on to the derived gates. So we saw already the list of 4 derived gates, isn't it? The very first one which we are going to see is NOR gate. Now, from the name itself, you can understand what is NOR. NOR is nothing but NOT gate plus OR gate. I told you the derived gates are basically made of basic gates, isn't it? Now, NOR gate is nothing but NOT plus OR. Now, the NOR gate has 2 or more input signals, but only one output signal, like other gates, except NOT gate, isn't it? If all the inputs are low, that is 0, then the output signal is 1. So in this, what is happening? When all the inputs are 0, only then we are getting 1 as an output. So see here, NOR operation is symbolized as X NOR Y. So if you are performing any NOR operation between two variables, suppose A and B, then how are we going to write it? A NOR B. And in other way, we can write it something like this also. Okay. So this is nothing but we are doing A or B, and then we are performing a NOT operation. So this together it's called as a NOR. Okay. Now see here, this symbol is nothing but our OR gate, and this symbol is nothing but our NOT gate, isn't it? So together they form, when we combine them together, we can write it something like this, okay? This is our OR, and this bubble represent NOT. So we are going to see bubble in many places. So whenever you see a bubble in any gate, this is nothing but a NOT operator, okay? So together when we do this, this forms our NOR gate, right? So it can have 1, 2, or 1, 2, 3, any number of inputs, but the output is going to be only 1. Okay. So if I'm giving A and B as an output, the output is going to be A plus B whole bar. So this is nothing but NOR. So if I'm giving A, B, C as an input, here it is going to be A plus B plus C whole bar, isn't it? If I'm giving A, B, C, D as an input, this is going to be A plus B plus C plus D whole bar. So this is how a NOR gate is represented. It is represented in this way. We should remember an OR gate with a bubble is called as a NOR gate. Now let's go ahead and see how the truth table is written for this. Okay. So we already saw that only for whenever there is two inputs are 0, only then the output is going to be 1. It is obvious, isn't it? Why? Because what is the truth table for OR gate? It is nothing but 0, 1, 1, 1, isn't it? Whenever we have either one input is going to be 1, then the OR is going to be 1. This is nothing but not of OR. So this is, what is this? We need to complement it. So complement of 0 is nothing but 1. Complement of 1 is nothing but 0. Complement of 1 is 0. 1 is 0, isn't it? So this is what is the logic actually. So you should remember for OR gate, both the values has to be 0, or how much ever the input. If there are 3 input, all the 3 values should be 0. Only then the output is going to be 1. Okay. Similarly, for a 3 input variable also, only here we have all the inputs 0. That is why we are getting 1 here. Rest all places we have zeros. Okay. I hope this is clear. Now let's go ahead and see the next derived gate, which is nothing but NAND gate. As the name says, NAND is nothing but NOT plus AND. Okay. NOT gate and AND gate together combined called as a NAND gate. Now here NAND gate has 2 or more input signal but only one output signal, right? If all the inputs are 1, then the output produces 0. Otherwise, it is going to be 1. So this is the other way of AND gate, isn't it? Usually, what is the method in AND? And what happens? What is the truth table of AND? Whenever there is either 1, 0 in the input, the output is going to be 0. Only when both the inputs are 1, then only we used to get 1, isn't it? But here it is complement of this. So complement of 0 is 1, 0 is 1, 0 is 1, 1 is 0, isn't it? So NAND gate is the complement of AND gate, right? So see here the truth table. So wherever we have 0, 0, 0, 1, 1, 0, if either so if all the inputs are 1, only then the output is going to be 0. Otherwise, it is going to be 1. Similarly, even in the 3 input variable, when all the inputs are 1, only then our output is going to be 0. Otherwise, blindly we can write as 1. So this is NAND gate. This is how a NAND gate works. So how do we represent the NAND gate in a logic form or a logical diagram? So see here, we have an AND gate here. Then we are adding the NOT gate. Together combined, they will form a AND gate. So AND symbol with the bubble is called as a NAND gate. Okay. So wherever you have to write a, if at all you have to represent a Boolean expression in the form of a diagram, and if there is NAND there, then you need to write this symbol, right? So this is for a 2 variable and this is for a 3 variable. So what is going to be the output here? It is going to be ABC whole bar. Okay. And here it is going to be AB whole bar. I hope this is clear. Next we are going to learn XOR gate or exclusive OR gate. Now what is this? Exclusive OR gate is something different. Okay. This accepts 2 or more inputs and produces single output like any other. Okay. Except NOT gate. The output is 0 if there are even number of ones in the input. If there are even number of ones in the input, then we are going to get the output as 0. And if there are the output is 1 if we have odd number of ones. So this you need to remember regarding the XOR gate. Here we are not using any logic, but if the number of ones are even, then the output is 0. If the number of ones are odd, then the output is 1. Okay. So this XOR gate is represented with this symbol, that is plus with the circle. Okay. So if at all you are saying we are doing the XOR operation between A and B, then we will represent it as something like this. So whenever you see this symbol, you should remember this is the XOR operation, because sometimes they might not give you XOR in the examination. They might directly give you this. Okay. So let's go ahead and see how do we write the truth table for the same. So truth table, we know if we have odd number of ones, then the output is 1. So here the number of ones is 0. 0 is nothing but an even number, isn't it? That's why we have 0. Here there are 2 ones, which is again an even number. That's why this is 0. Wherever there is odd, see here it is 1, 1. That is why we are getting the output 1. So this is XOR gates truth table for 2 input. Now let's see what is happening in the 3 input XOR gate truth table. Okay. So here the number of ones are even. That's why we are getting 0. Here it is only 1. 1 is there. That's why the output is 1. Here again 1. So output is 1. Here we have 2 ones which is even. That is why the output is 0. Here again only 1. 1 which is odd. That's why 1. And then there are 2 here, there are 2 here, there are 3 here. 3 is again odd, isn't it? That's why our output is 1. So this is XOR gate. If you have even number of ones in the input, then the output is 0. If we have odd number of ones, then the output is going to be 1. Okay. So how do we represent this one, the XOR gate, in the diagrammatic form? So this is how we are representing XOR gate. Okay. An OR gate, it is going to be an OR gate with a double curve in the beginning. So this is going to be 2 variables. So how are we going to write it? A or B. Okay, if it is 3 variable, we are going to write it as A XOR B XOR C. If it is 4, then we are going to write A, B, C, D. So this is going to be A, B, C, D. Right. So this is how we are going to represent. The symbol you should remember. How do we write the XOR? Okay. So see here, XOR addition can be summarized as follows, which is 0 XOR 0 is 0, isn't it? 0 XOR 1 is 1. Why? Because we have only 1 1 here. 1 XOR 0 is 1. Again, we have only 1 1 here. 1 XOR 1 is 0 because we have 2 ones here, isn't it? So this can be summarized as X XOR Y is nothing but X bar Y and XY bar. Okay, so you should remember this. How do we represent the XOR operation? So any operation A XOR B can be represented as A bar B plus AB bar. Okay. Now let's see XOR gate or exclusive NOR gate. Now we have seen XOR. So whenever we add a NOT to this, it becomes XNOR gate. Okay, or this is also called as exclusive OR gate. Now when XOR gate is followed by a NOT gate or inverter gate becomes XNOR gate. Okay, so NOT of a XOR operation is nothing but XNOR. Fine. So in the truth table also, it is going to be the whatever the output we were getting for XOR gate, this one is going to be the complement of that, isn't it? So in this case, what is going to happen if we have even number of inputs in the even number of inputs as 1, then we are going to get 1 as output, and if we have odd number of ones, then we are going to get 0 as the output. Just the other way of XOR gate, isn't it? So see here, whenever we have even, we are getting 1. Whenever we have odd, we are getting 0 as a output. Similarly over here. So how was it for XOR gate? XOR gate, we had an input 0 here because we have even number of ones. Then we had 1 here because we have 1 ones. So even number of, odd number of ones, and this was 0. Now what is this? This is nothing but XNOR, isn't it? So XNOR is complement of this one. So zero's complement is 1, 1's complement is 0, 1's complement is 0, and zero's complement is 1. I hope you're understanding this, okay? So XNOR is nothing but a complement of XOR gate. So we are just adding another NOT gate to the XOR gate, and we are going to get the XOR gate. So this is how it is going to be represented. How do we write a XOR gate? A curve and a OR gate, isn't it? Now when we add a bubble to it or a NOT gate to it, so in short we can write it something like this. Directly we can write a bubble. This is nothing but a NOT. Okay, so this becomes our XNOR gate. Right. Now see here, the expression representing XNOR may be written as, how do we represent? So another thing, the XNOR is how XOR was represented, something like this, plus with a circle, isn't it? Now XNOR is going to be represented as circle with the dot. Okay. Now this one can also be represented as X bar plus Y, X plus Y bar. This is also another way of representing the XNOR operation. Okay. So you should remember this expression, because sometimes if you are asked to derive certain expressions, and if there is this symbol, then you should know this is nothing but X bar plus Y and X plus Y bar. Similarly, you should also know this is nothing but X bar Y plus X Y bar. This is important for you all to remember. Okay, so this is all about the basic gates and derived gates. We have seen today what do they mean, how do we represent them diagrammatically, and what are the truth table values are going to be. So we have seen 3 basic gates and 4 derived gates. Okay, so in the coming session, I'm going to show you if there is a given Boolean expression, how are we going to draw the circuit diagram for them using these gates. And also further, we are going to learn about universal gates. Okay. Till then, students, thank you for watching and take care.